Okay. Questions before we start? Any questions? Okay. So we were discussing Q learning. Should I put up the slide? This also. Yeah, so we were discussing Q learning, which is basically active version of temporal difference learning. Okay, and we were discussing the fact that that unless you keep track of Q values, you cannot actually figure out what action to do. Okay, and then if you do keep track of Q values, then in essence what you're doing is for each state you, instead of previously you were just remembering for each state one single value called V of S, okay, and you are updating it during temporal difference learning. Here you are actually going to keep track of multiple values called QSA, which is the Q value of doing action A in the state S. And this you can think of as the value function is essentially being separately kept. So for example, for this particular, in this picture, I assume you realized that this basically says if you do the action of going right, then you have a minus 0.43. If you do an action of going left, you have a 0.42. If you have an action of going up, you have a minus 0.51, going down 0.15. Okay, that's the current expected value of doing that action. And the thing that I asked you at the end of last class is that when you have those Q values, then the value of the state is just the max of the Q values. There is no expected value, right? Basically, you have a choice and you will always pick the action that has the highest Q value. If nothing else makes sense, right? Okay. So basically, you're just going to, instead of updating V values, you will be updating Q values. Okay, and it turns out that the update equations are fairly straightforward, and then you essentially, just like in the temporal difference learning, you're updating the V value. You're going to update Q values now. That's it. Okay. The one difference between temporal difference learning and the Q learning is that Q learning is active learning, which means something else. In addition to updating the Q values, you need to decide what action to do. Right? Okay. You have your current approximation of the Q values. So for example, let's say the agent has this is its current approximation of the Q values. Suppose it finds itself, let's say, in this place right here. So then what action is it supposed to do? What? Go right. Always go right. So that means, okay, so my question is, remember, this is at some point of time during the learning phase. So these are not Q star values, these are the Q values. Right? Okay. Until they converge, they don't become Q stars. They're just Q values. Okay. And given that, the question is, so what was the question? I mean, about active learning that we talked a lot about last class.
You follow the policy of the policy of the technology switch.
Exactly. So you don't want to do the greedy thing all the time. Because these are not the true Q values, you should not be greedy all the time. Okay. So you would still, even though, so basically behind it all, you still have the exploration policy. The exploration policy should be, sort of epsilon greedy. Remember, there are variations we talked about for multiple types of exploration functions. All of that carries over here too. Without that, Q-learning won't work. For the same reasons, it won't work for the model-based active learning. You see what I'm saying? Okay. So I mean, we won't mention this, but I mean, it's not mentioned explicitly in the next slide, but it's understood that if it's active learning, you need to essentially not be greedy, and you need to have an exploration policy. And in this particular case, the exploration policy will correspond to saying, pick the Q value, pick the max Q value, the action, and then do that action with, let's say, probability P, and with probability 1 minus P, you do a random action. That's one idea. There's also other ideas. The other idea, the more sophisticated idea, for example, was to think in terms of U plus, right? Similarly, you can think in terms of Q plus, which keeps track of how many times you have come to a particular state and tried that action there. And then if you have tried that action a large number of times, then essentially you are going to be more greedy. If you haven't tried it often enough, then you will be less greedy because you want to explore more. My only point is that Q-learning, is, so that there is a difference between passive versus active learning, and there's a difference between model-based versus model-free learning. And these are orthogonal differences. Okay, you can have model-free passive, you can have model-free active, you can have model-based passive, and you can have model-based passive. Okay, and whenever you do active learning, you need exploration policies. Okay, that's the thing that you want to keep in mind. Okay, so now the Q-learning basically looks very much like temporal difference learning. Okay, once again, what you're doing is you're updating based on the sample that you actually experienced. So you are in some particular state S, okay, and you did some action, whichever reason you did this action. You could have did this action, you could have done this action based on a greedy policy, or you could have done it based on an epsilon greedy policy, or you could have done this action because of, just random policy, right? Okay, if you basically, after you do this action, you got S dash. Okay, so now you essentially had, previously you had QSA was the current estimate of doing action A in S. But now that you actually did this, you got S dash. Okay, so the sample that you really experienced was this. Okay, notice what happened here. So the sample that you really experienced here is because you did A and you went to S dash, of course you got the reward of going from S to S dash using A. And then at this point you will get the value of S dash, the current estimate of the value of S dash. And the current estimate of the value of S dash is just the max of the Q values of all the actions. Do you see what I'm saying? Okay, notice, so this is actually interesting because you don't quite know what action you will wind up doing there. Okay, you're just saying that I'm basically, if I'm reaching here, then I'll assume my current estimate of the value of S dash is accurate enough for me. Okay, and that is just the max of the Q values. And I multiply that by gamma, add it to the reward, then that is really what I think is the value of S. Okay, And I also have another value of S, which is this estimate. These two estimates have to be nudged together, nudged closer together. Okay, so what I do is I set Q of SA to be the old Q of SA plus alpha times my new estimate of Q, Q of SA, minus the old estimate. So that means basically I'm just pushing it together. As long as alpha is small, then you're making small changes in the Q1. Yes, sir.
What's V star function?
What?
The V star function.
No, V star is, I'm sorry. V star is the value function. V star is the value function. This is the problem. We haven't yet had an exam, so I have no clue where anybody is, essentially. So, V star is, any star means optimal. Okay, V star is the optimal value function. An optimal value function is connected to the optimal Q function. Okay, yes?
So R of S, A, S dash is not something that you already know, it's something you experience.
You will experience, exactly. Again, these algorithms are very simple, but there is a lot of, you want to make sure that you understand them. In fact, things will become crazier in the rest of today's class because I will use a technique which can be seen both as a reinforcement learning technique and as a technique for solving MDPs efficiently when you know the full model. And if you know the full model, why do you need reinforcement learning? You don't. But I was telling you last time that sometimes even when you have the full model, you may want to be lazy and act as if you will learn from the full model. Do you see what I'm saying? Okay. Actually, lots and lots of things are related to that idea. So for example, if you have a big textbook, why even come to classes? The reason you show up for the classes is because you somehow think I'll give you a sample from the textbook so that you don't have to read the whole textbook. Okay, if you read the entire textbook, you understood the material already. Okay, and similarly, we will look at a version of an idea called RTDP, which is both a reinforcement learning technique and a technique for solving MDPs fast. But the point, the reason I brought that up is I want you to think the questions that you're thinking, which is, if I know at this point, do I know the model or do I not know the model? Okay, if I know the model, then essentially this would just be a table lookup. If I don't know the model, then it will be an experience. Okay, now this will never be an experience. You do not experience the overall value, long-term value of a state by just being there. If that was to be possible, all of us would be highly intelligent. Right? Okay, we had to learn by working very hard. We had to learn that even though this state looks kind of depressing, from this state you can get to really, really nice states over a long period of time, because of which its backed up value is quite good. And so backed up value is something that you must always keep track of. And this is a table lookup, this is an experience. And that's a very good question to ask yourself. Okay?
So what is alpha in there?
Alpha is the learning rate. It's basically how much are we pushing. This is basically, by the way, this stuff is just the same as temporal difference learning. There's an alpha in temporal difference learning too. That's the learning rate. That is how fast, how eager are you to push yourself to be equal to your neighbor's value.
The question is then, shouldn't alpha be updated constantly? Because we are kind of learning that our neighbor is, let's say, rich or poor in this instance, but which might be false, and which, when it propagates to the neighbor.
So your question is, can the learning rate itself be changed? That is feasible. Although if you keep the learning rate small enough to begin with, then you are guaranteed convergence. Okay, the learning rate itself can be changed. Again, those of you who have any background on like neural networks, for example, you may know that this sort of thing happens there. The weight changes are always done in this alpha fashion, and the alpha can be varied over time. That's a good point. But here, for simple scenario, I'll just assume in this case that the alpha is set constant. Okay. Okay, so that's Q learning. Okay. So we have talked about, as I said, four different, two dimensions: model based versus model free, so and active versus passive learning, right? And so those are the two. We showed this in the beginning of the reinforcement. This is sort of the end of the reinforcement learning part, and then I'm going to move on. By the way, reinforcement learning homework has been given, right? So anyway, so passive versus active, you should understand what are the relative advantages. Yes. Oh, okay, good question. I'll send you an email about that. Okay. I won't be here for sure. Okay, so, but whether there's a midterm or not, I don't know yet. So actually, originally I was thinking I'll have a midterm because I'm not going to be here, but I don't necessarily know that has to be done, because in fact, I think it's also fine. My other idea is that I'll just make you watch the videos for the corresponding lectures from the last year. So presumably if I take a vote, we'd say just watch. Okay. So maybe I'll make you guys watch 2 videos when I'm gone, and you wouldn't mind it. So anything to avoid the midterm, which is fine, because then I would basically come back and then have the midterm. That's more or less what I'm thinking of right now. Okay, so I will essentially, we will do whatever we do until next Monday, and then at the end of Monday, I'll tell you which parts of the last year's videos to watch. So I would know exactly where I stopped, and it'll be probably more than one video you would watch. There's also fall break coming, because we'll miss the next Monday after that too. So maybe I'll just say from there onwards to the end of the semester, and then we'll meet. Okay, that's the idea. Okay, so model-based versus model-free, passive versus active. You understood both of those quite well, and now the other thing is the other thing that we did not talk as much last time, which you also can understand right now, is the extent of backup. Okay, so that is the picture. So in fact, let me see if I can get you that nice picture. Okay, so this is a good picture to keep in mind. So on one hand, this is basically you're talking about whether the kind of backups you are doing, okay, are they temporal difference style backups, which means I change my value based only on the single neighbor I have watched, or full dynamic programming style backups. This is actually very important, because we'll be talking about this when we talk about RTDP. So here is the idea. So if I have some state S here, and in the current particular sample that I just did, I did an action A, I got S dash, and so I experienced, basically I got the reward plus gamma times V of S dash from here. Okay, but this is not as if these are the only numbers I remember. Okay, in fact, this state is also connected to other states, and I know the current value estimates of all those other states. Right? Okay, so one of the questions is, why am I only changing my value to be consistent with S dash's value? Why don't I really change my value to be consistent with all my neighbors' values? What does it mean to change my value to be consistent with all my neighbors' values? No, if I have, basically, so the idea is I did an action A here, and I got S dash. Had I known, for example, that when I did S, when I did A from S, I actually could have gotten either S1 or S2. Furthermore, even though I did A right now, I could have done actually A dash. If I did A dash, then I could have gotten either S5 or S6. Or I could have done A double dash, in which case I could have gotten S7 or S8. Suppose I have all this information, right? Suppose I have all this information. Then in this particular case, I did action A, got to S2. Okay, so that's a sample I experienced. But I also have all this information in front of me. If I have this information, what's the best way to reset the SS value?
If you're considering all of the neighbors,
These are the only neighbors, yeah, exactly, all these neighbors, yeah.
it's like you're exploring all the neighbors.
I know. So, but the point is, how is my value connected to my neighbor's values? Oh, give me a break, guys. What? What? I know, so what is the name for that? Bellman backup, right? It's just Bellman backup. You should be asking yourself, why haven't we talked about Bellman backup for such a long time? Right? I mean, you cannot be in MDP and reinforcement learning without saying Bellman every few minutes. And yet, for 3 days, probably 2.5 classes, we haven't said Bellman. What did we do? Why did we not do it? Actually, in fact, it turns out we are using Bellman backup in coming up with our updates, right? Because even when we are doing Q learning, etc., right? This is a Bellman equation. This is a Bellman equation. It's just that you assumed in this case that you are only getting one sample at a time and you are not keeping track of either the model of the actions or the rest of the neighbors. In which case, if you just keep pushing your value closer to your observed neighbor's value, then if you keep doing long enough, then that would be like essentially doing Bellman update. You see what I'm saying? This ultimately is the thing that you need to understand, that essentially what temporal difference learning is doing, or what Q learning is doing, is it's doing one Bellman up, what you could have done in one Bellman update, it takes many temporal difference updates. You got that? Write it down somewhere. Okay. One Bellman update is like doing many temporal difference updates. Okay. And so basically that, and why did we not do Bellman update? Why did we not do Bellman update? Why did we just go with the temporal difference update? Why is it that we are looking at only this and not this? To do this, you need model. Now, if you do have the model, why just do this? Why not do this? Faster in what sense? I mean, basically, there is this issue of per iteration, this is faster. The number of iterations taken is higher here. And per iteration, this will be harder. It will be slower, but the number of iterations taken will be fewer. In fact, if you look at that picture, and if you can realize that you have seen this algorithm, you have in some sense seen this algorithm. That was ADP. That was approximate dynamic programming. Given the current model, do value iteration using the current model. When you do the value iteration, then you did Bellman updates lots and lots of times until it actually converges. Then you know your best possible understanding of what your value is given your neighbor's values. right? So the interesting thing is when you have model, when we had model, we use this. Approximate dynamic programming. Approximate dynamic programming is value iteration or Bellman update star. Do Bellman updates until nothing changes. When we did not have model, we shifted here. Right? And said, since we don't have model, we'll just do temporal difference learning. But we actually also considered this, which is Monte Carlo. Okay, where you expanded your experience until multiple steps, and then you backed up the experience in that one single trace. Okay, so if you look at this and this one is essentially considering. So both this and this essentially are looking at only the sample that you experienced and are using only the sample you experienced to update. This and this are using the sample as just one piece of the equation. I understand I just now felt that this side is looking good, but then I also have my idea of how my other neighbors are in terms of my current V, current estimate of the V values. Okay, and then I will use all that to update my value. And here I just did it in one step update. Here I did multi-step update, or basically full ADP. Okay. And in terms of the temporal difference, in terms of the experience here, I just did, without having any model, I did either one step return or multi-step return. Or we also looked at TD lambda, which is considered a multi-step return, but actually back it up as if it is a weighted sum of many partial step returns. You see what I'm saying? Okay, now, if you are doing really reinforcement learning, then you have first a question of, do I want to be model based or model free? Okay, and if I'm doing model free, I don't get to do this and do this. So I only get to do this or this. Next, after this, I will say, I have an MDP. That means I know everything about it. I want to use a reinforcement learning method because I'm lazy to solve the MDP fully. Okay, so if I have the full MDP, the normal idea would have been to do this. Because that's sort of like the, yes, sir.
I'm having trouble with you saying this, knowing which one you're talking about.
Oh, I'm showing, I thought I should. I'm looking right now, I said this. Sorry. Okay. I think when I touch, I guess you don't see it. Sorry. That's the problem. Okay. So, yeah. So I'm basically saying if I have the full MDP model and I still decided to do reinforcement learning, then it turns out all four are reasonable possibilities for me. Do you understand what I'm saying? Okay. If on the other hand, I really don't have the model, this is a true learning problem, then I need to decide whether I'm going to just learn the policy, which is, if that's the only thing I do, I want to do model free, or learn both the action model and the policy, in which case I will do model based learning. If I'm doing model-based learning, then those are my options. If I'm doing model-free learning, these are the options. But if I have the full MDP and I'm just doing RL as like a way of avoiding hard work, then either of them are options. The reason I bring this up is because the next topic is solving MDPs approximately. And we will use an idea called RTDP. Which sort of looks it's sort of between this and this. By the way, there's a spectrum here too. So this is one step return, this is n step return. You can do k step return in the middle. And similarly, this is dynamic programming with just one level look ahead. This is a full dynamic programming. If those of you who know game trees, right, this is one ply game tree. This is all the way down to the bitter end, where everybody has actually is a a leaf node. Okay, and here would be k-step look ahead in between. Okay, so what we will be doing is, in some sense, actually, we'll be looking at an approach called RTDP, which sort of falls right here. And while you are thinking about it, you get to think both about learning and about inference at the same time. You can think of RTDP either as a reinforcement learning algorithm or as an algorithm that just is used to solve a known MDP approximately. Okay? Any questions? Okay, that's that. Let me just. Yeah, go ahead.
So in key learning, when we're just getting started and we have made our first action, what do we consider it as the max key value of our neighbor? It's the first one we just get started.
Basically, you initialize, right?
Just pick something.
Yeah, you initialize. In all these cases, you start by initializing the value function or the Q function to anything you want.
Okay. Same as we did.
Same exactly. Okay. So, I mean, the thing about this whole discussion is I can make you think, you can actually make yourself think that by looking at the discussion of reinforcement learning algorithms and MDPs, that at some level you can understand it very quickly and then move on. But then if you ask questions such as the kind of question he was asking, do I experience this or am I looking it up on the table? Those are exactly the right question to ask yourself. That is the second level understanding. That's when you will actually be able to apply it, because you can use these approaches either for actual inference or for learning or a combination thereof. Okay. There you go. So we are, if I can somehow get here. So what we will be doing in the remaining, in this next topic, it's actually a topic change now, okay? So until now, we looked at MDPs, and we looked at classic MDP approaches, value iteration, policy iteration, both of which just try to find the exact policy, exact optimal policy. Then we looked at reinforcement learning, where we are not given the model and we are still interested in finding the optimal policy, and we do it asymptotically. Now, the thing that you want to remember is MDPs, finding the policy for an optimal policy for an MDP can take time. Learning the optimal policy by reinforcement learning can also take time. So what's the difference? Both of them are taking time. What?
How much time?
Yeah, fine. How much time it does? I mean, so is that the only thing that we are comparing reinforcement learning and MDP approaches on?
The best policy.
I mean, why is one reinforcement learning, the other is just inference? Yes.
I mean, fundamentally in MDPs you have the model. Where
Yeah.
in reinforcement learning you don't have a model, so you have to have a simulator.
Not just simulator, you need to execute. So the time, saying time is kind of misleading. Okay, what time are we talking about? And an intelligent agent spends two types of time, lots and lots of types of time, but at least two types of time. One is deliberation time. The other is execution time. MDPs don't have to do any execution time. That's the whole point. They have everything in front of them. They don't need to execute. Okay? Whereas they do a lot of deliberation time. A reinforcement learner does both execution time and deliberation time. So if you take, for example, an ADP-based reinforcement learner, it's experiencing the world, with the samples. So that's the execution time. Okay. Plus, once the samples come, it then is running sort of a value iteration. That's the deliberation time. So that's why reinforcement learning sort of combines both thinking and doing together. It's much more closer to the full AI, right? It's both thinking and doing. Okay. Now, the interesting thing, of course, is the execution time can also be made into simulation time. If you have the model and you don't want to use the model, you would just simulate it. As and when you need, you just check, what would happen if I do this. Okay, you ask the simulator. That simulator will only just give the answer, not the probabilities, nothing. Okay, now if you do that, then you can actually come up with MDP algorithms which do some amount of deliberation time and some amount of simulation time. And those algorithms can be both used for MDPs and for reinforcement learning. If you consider simulation time, execution time, it becomes reinforcement learning. If you consider simulation time, it becomes MDP. Okay. So that's one important way in which you can get efficient algorithms for mark-coordination processes. So let's back up one bit and say that the reason you need efficient algorithms for mark-coordination processes is because you can have MDPs which have very large number of states. And we know that MDP algorithms we have seen are polynomial in the number of states. If you have exponentially many states, then being polynomial in exponentially many states is still death knell. Okay, so then the question would be, you say, well, I don't want optimal policy anymore. I just want to do close to optimal. Okay, so I want to find the right thing I need to do for the states I'm likely to wind up in. In fact, one very important issue in MDPs is, in the case of MDP, value iteration in particular, if you have a billion states, in value iteration you update all their values once, all their values again, all their values again, and so on. Now, if you happen to know that you're starting from one particular state, there may be a higher probability that you will be in certain sets of states, irrespective of how you behave, and much lower probability that you will be in some other faraway states. It's more important to know what to do in the states you find yourself in, and less important to know what to do in the states that you don't expect to find yourself in. You see what I'm saying? Right? Now, the beauty of this is that, so this is a way of approximating. This is the way of approximating. Okay, so we will come up with algorithms that essentially will find partial policies, which will tell you the right thing to do in the states that you are more likely to find yourself in. And I would say that's good enough for us. Now that's what we're going to do now, and mostly because without that, we don't even have a chance of actually computing the entire policy. However, we should keep in our mind that there's always a difference between optimum and approximate. Okay, my best example for that is who, in their right mind, trying to learn how to fly an airplane, would figure out what's the right thing to do when the birds take away both your engines and you are on top of a big city like I guess Manhattan, Southern Burgundy. Okay, so that's why he's a hero kind of a thing, because he actually did more than what is required to fly the planes most of the time. Do you understand what I'm saying? Most people don't quite know what you're supposed to do and how to glide this huge flight with large number of people and land on Hudson River. You know, a normal value iteration will figure that out for you. The reason you won't do it is because it's just too costly. You know, if you have to figure that out as well as every other state's optimal action, you would never figure out the optimal actions for the states that you're more likely to find yourself. So while we will, for computational reasons, focus on suboptimal, approximate policies, you have to keep in mind that what you're losing is Sullenberger. Okay, because if it's not optimum, then I can always come up with a scenario where you will reach catastrophic decisions, catastrophic end, essentially. I mean, saying that I know exactly what to do in 99.9999999% of the states where I'll find myself in. I know exactly how to fly the plane. Is not going to be helpful when you find yourself in that 10 power minus 7 probability state. At which point you don't know what to do, okay? But that's the chance you take when we do what we're doing. Okay. So anyway, what we're going to do is this idea of real-time dynamic programming, which, again, I put this picture again here. I think of this as what I would have done. So in all this discussion, act as if you have the full MDP. And the first part of the discussion, we basically, and then okay, so let's assume that you have full MDP, and you could have done this, which is the full value iteration or policy iteration, but we choose to do essentially something like a modified update, which is better than temporal difference and Monte Carlo, but and it does use the model. Because I have the MDP, I have the model, so I can use either this or this. Okay, and the idea for this is called RTDP, real-time dynamic programming. The idea is sometimes the agent finds itself in a particular state and doesn't get to say, okay, let me think about the optimal policy. And having figured out the optimal policy, I will also know what I'm supposed to do from this state. That will only work when the world is static. Until now, actually, we are assuming the world is static. The only thing we extended from A-star search is the world is still static, but it is stochastic. But really, of course, the world is not static most of the time, and it's dynamic. And if it's dynamic, and then you say, well, my planning time is not supposed to count towards my execution time. That's like saying, the exam time, I get to think first. And then I'll just, the extra hour that you give me, the hour for the exam is only for writing down my answers. You should, question me when I'm thinking. That I can take as much time as I want. That's not the way. We combine deliberation and execution time together into one set of units. Right? Okay, so the question then is, you will not be able to do this in real time, clearly. So that's like the original motivation. So you probably have to just do k-step look ahead. Remember, this was also like the motivation for limited look ahead min-max that game trees use. If you have a lot of time, you should just go all the way down to the leaf nodes, where every node is a known draw or a win or a loss, and then back up. Then you will know for sure what the right action is. But if you don't have that much time, then you just go k deep, k apply deep, and then send back up your values. Okay. So the original motivation is agent acting in the real world, and in essence, the way the agent would do is it sort of, kind of, does this, except we'll see that you don't necessarily have to construct the tree. We will. There are these notions called RTDP trials that I'll show you in a minute. And one of the interesting things is those trials look almost like these Monte Carlo trials. The difference is when a Monte Carlo trial is done, all you are doing is this guy's value is nudged a little closer to the value of the immediate neighbor or the immediate k neighbor. Whereas what we would do is, since we have the model, we would essentially do the full Bellman update. Every time you simulate the execution of an action and you find a particular state, then you will essentially do a Bellman update because you know everybody else's values and you know all the actions you can take. So you actually compute the R of S plus expected backup for each action based on the current values. Of all these values, one guy's value has changed, so you just end up getting approximately a new value backup. See what I'm saying? Okay, so that's what we'll see in a minute. And then you perform Bellman backup on the visited states. Doing Bellman backup would not be possible if you are model free. Right? If you're model free, how are you going to decide how to do the Bellman backup? Okay, and then you stop basically when you hit the goal. Okay, for each trial, and then you do this trial multiple times. By the way, this notion of goal, that is not saying each experience is going all the way to a terminal state. Okay, and for this discussion, actually, we will look at SSPs. Remember, for 3 classes back, 3 or 4 classes back, we talked about stochastic shortest path MDs, which we convinced ourselves are more general than infinite horizon or finite horizon MDPs. And stochastic shortest path MDPs do have a known node called the goal node, a unique node called goal node, and once you reach that, you don't get out anywhere. So during your simulation, you are trying to reach that. Whenever you reach that node, you say that's one type, and then you do that. Okay, and every time when you do this, I'll bring down backups. Remember that in value iteration, you bring down backups. Many times. The way the value iteration backups are being done is synchronously. Everybody around your neighbors update your value. Then everybody around your neighbors update your value. That's what value iteration does. Here we are saying you only update the values of the states that fell on trace. You see what I'm saying? Now that means if in fact there are states that are like basically losing privileges because there's privileges that are so unlikely, then you're in simulation very unlikely. So you won't be wasting time updating the value of the unlikely states. That's the speed up you get. Okay. So that's RTDP. Let me give you an example, and and then basically RTDP converges in the limit of number of trials to infinity, because that way you will eventually, if you keep doing these trials, everybody would be touched. And so you can think of RTDP one way as a prioritized sweeping algorithm. Remember, for value iteration, I talked about prioritized sweeping. That means not everybody has to update their value at every iteration. You have to update the value of the guys who are important. And you might define what importance is. This is one way of importance. The ones that are likely to occur in an arm of sample of your behavior are more important. And those are the ones you will update the values of. The ones which are very, very unlikely will occur very, very few times. And so they won't be updated as much. At number of trials to infinity, RTDP is the same as value iteration. However, if I am stopping after some arbitrary amount of time from the beginning, value iteration may have spent that 3 hours wasting its time both on completely useless states that you may never really reach with more than 10 power minus 7 probability, as well as states that you are likely to reach with close to 30% probability. And it gives the same amount of attention to all. Whereas the RTDP on the other hand would have spent more time on the ones that are more likely. And the cute thing is because it just naturally focuses on important states, because those are the states that you see when it simulates the model. So it starts from a state. Okay, it's not that basically the RTDP actually uses the fact that currently the agent is at a particular state and it's trying to figure out what to do. So it will always do the trials from that state onwards. So there's a known initial state. Okay. Okay, so here is like an example that I'll just run through. So this is an MDP, okay, and I just drew it more like a graph. Okay, the idea is these are the actions, and so from this S I can go to this action or this action. If I go to this action with different probabilities, I can go to this state, or this state. I'm sorry, this is what I think you're saying. So, well, very nice. Yeah. So if I'm here, if I do this action, I can get either this state or this state or this state. And those all have different probabilities, and I know those probabilities. I know them. That's what I was. Okay. And similarly, if I'm in this state, but while I know these probabilities, I'll assume that I put those probabilities away in a model, and I called it simulator. Okay. By doing that, what I get to do is, if I actually don't have the model, then I would get the simulator done by really doing the work, doing the action in the work. If I have it, then I use the simulator. So if I write an algorithm such that it doesn't touch the model other than by making calls to a simulator, then you can replace the simulator by real world and become reinforcement learning algorithm. Yes?
So this is referring to something you said a couple of classes back when we started on active learning. You said it's important to not follow a given policy so that you may miss out some states where are high rewards. So in this topic, you're saying that it's not useful to explore all the states. So I find that's a confusion.
Yes, that's the confusion, which is basically Sullenberger is important, so is getting your pilot's license before you die. I don't know if you understood what I just said. Right? In the sense that if we all can live for infinite number of years, then essentially the right thing to do is figure out what to do in every possible, what's the optimal action to do in every possible state you can possibly encounter, even if it's only 10 power minus 12 probability. Okay, but on the other hand, if I tell you, once you kind of done with your pilot's training, you get to fly the planes and actually get money, then you don't have the luxury of saying, I'm not done yet. So when you have to stop yourself, all I'm telling you is at least stop yourself having figured out what to do for the states that you're more likely to encounter. Even though if you're the most unlucky person in the world, then you will get the state that's very unlikely to be encountered, but you still encounter it. I mean, that's a very good question, and I hope you get that question and you got what I'm saying as the answer, which is, I'm not telling you that the right thing to do is to ignore parts of the world. Okay, I'm just telling you that if you have to ignore parts of the world because of computational considerations, ignore those parts that are less likely to happen. You see what I'm saying? Now, the interesting, one very interesting thing, of course, is a second order point to what you're asking, is here I do have the entire model in front of me. Okay, whereas in reinforcement learning, it's just I'm actually asking the world. I mean, I'm just doing actions in the world. Correct. Okay, but other than that aspect, it is the issue is you have a computational restriction and you had to focus on some states, and you may as well focus on the states that are more likely to occur. You couldn't have done any better by focusing on the states that are less likely to occur. Yes.
How do you know where to set your threshold for more likely versus less likely?
The good part is the states that show up are the ones which are more likely. I mean, that's the beauty of this idea. You're letting the world tell you what parts of the world occur more often. You see what I'm saying? Okay. So let's play with this picture. So I have a state and I have these actions, and let's assume that I'm starting from this state, and let's assume this is my goal state. Okay. So ultimately, all the traces have to end up in the goal state. Okay. So what do? I start, and I'll assume that everybody has a value currently. It's just initialized, maybe zeros, except for the goal state for which you know the value. And then what I do is I start from a 0. Based on my values, I greedily select an action. Okay, I greedily select an action based on the basically the Bellman backup idea. That means, pick the action that will take me to the neighbors that currently seem to be the best neighbors. And I do that action. When I do the action, if I'm doing reinforcement learning, I'll have to actually work in the world. I have to, do this action in the world. If on the other hand, I have the model, then I just call my simulator and tell me, okay, I'm doing this action, tell me what will happen. And the simulator has the numbers for this. It says, oh, this is 0.3, this is 0.4, this is 0.3. So it will actually toss a coin and tell you which happened. From the point of view of this algorithm, whether you are actually executing this action in the real world or whether you're just simulating is immaterial. From the point of view of whether or not you will live to do the next action, it of course has an important impact, because when you do execute, you could actually have gone into a very bad state. Whereas if you only simulate, you say, oh, I could get into a really bad state, and you will live to see another day. That's the big difference. Okay, so I will continue in this case. Let's say I pick this action, I guess. So start at the start state. I'm going to repeat, perform a Bellman backup. So upfront, basically set my value to be the max of the expected values of all the actions I can do. Okay, that's the Bellman backup. And then, and to do that, remember that essentially in this particular case, remember that to be able to update S0's value, I was touching the values of all these guys. Right? Because that's what you look up. So essentially, you say A basically can get me to this state or this state, this with 0.4, this with 0.3. So 0.4 times H1 plus 0.3 times H2 plus 0.3 times H0 is what this action will bring me. Right? And similarly, I can do it for this action. When I'm doing update, I'm basically using my current value information. Okay? And then, notice of course that when I initialize upfront, basically these guys' values could be far away from their true values. However, when I reach the goal state, when my trace reaches the goal state, the guys near the goal state, just like in the value iteration, would start having their true values. And so the message propagates. So again, RTDP is really doing value iteration. Instead of doing entire synchronous value iteration one step at a time, it's doing value iteration on traces. Okay? So the same idea again. So I perform a Bellman backup on S0, then I got the value for S0, and then I simulate. At this point, I pick the greedy action. Let's assume the greedy action is this, apparently. That's what I picked. So I need to simulate. I know that when I do this action, I'll have either this or this. Okay? And let's say this is 0.3 probability, this is 0.7 probability. Even though I didn't write it, this is known to my simulator. These numbers are known. That's what knowing the model is supposed to mean. If I don't know the simulator, then I will actually do it in the world knows. Okay? And then when I do this, I basically figure out which state actually occurred. So supposedly S3 occurred. Okay, now simulated greedy action. So S3 occurred. At this point, I update the value of S3 using Bellman backup. Okay. And now I once again look at the best action from S3 and simulate. In this particular case, S3's best action is supposed to be this, and this has only, it's a deterministic action, right? In the picture, there is no branch from the action, so it's a deterministic action. So I guess you don't really have to simulate. It's like a one-sided coin. It'll always come heads, okay? And then you got to S6, and then from S6, you again do the Bellman backup, and then you pick the best action from S6, and you reached, and you simulated again. This is the best action presumably. This is the best action presumably, and you simulated. You got to SG, and that is one trace. Okay. In doing this trace, notice only this guy got updated. Right? Okay. Now, just before you went to SG, S6 realized that it wasn't a particularly bad loser. Do you see what I'm saying? Before, S6 had this initialized value, but then when you came to S6, you updated S6 value based on value iteration, the Bellman update, then it realizes SG is one of its neighbors, and so it actually starts feeling good. So it has a better value. And that message will traverse, back up the tree. Yes? Okay, that's a very good question, and this picture is misleading, but if you do hit a sync state, right? There are two issues, of course. Okay, if you do hit a sync state, then you basically start back from, you can assume that the trial is over and restart again. And in that case, it does matter whether in fact it's a reinforcement learning approach or a simulated approach. Because if you hit a sync state in reinforcement learning, then you don't get to start all over again. When you die, you die. Okay? Whereas if you are actually simulating and you reach a sync state, okay, I reached a sync state, I'll start all over again. Okay, that's point one. And point two is that we are actually talking about SSPs. This is like a second order point. In SSPs, we carefully made sure there won't be no sync states. Do you see what I'm saying? I mean, both are important points. I mean, if you do have an MDP where there are sync states, and if you're using simulation, you'll be fine. But if you're talking actually about SSPs, then you don't need to worry about any sync state other than the goal state. Okay, yes?
You're always choosing variably here, right?
Yeah.
So aren't you having the same problem as before in that?
It's a lovely question. I mean, there is something called a forum for this class. And if I was taking this class, I would be hitting my head and asking all sorts of these questions. Since there were no questions, I assumed you're all wise, okay? And that you understood all these things. You thought through this, nirvana happened, and you come to the next class when I ask, are there any questions? There are no questions, because you understood everything. But that's a great question. That should keep me awake. There are many such questions in whatever happened until now, seriously, okay? It's a question of how much are you willing to ask, other than let's just let him talk and move on, That's a very good question. We will, first of all, there are two different issues here. One is that, so in fact, we will look at a way of making it non-greedy. Okay? But when we do that, what we'll wind up doing is it sort of looks like the exploration exploitation issue. Okay? Except you know the entire model here. Right? It's just that, it's like, I know the book. The book is right here. It's just, I'm not looking at it. Okay? So the exploration, exploitation, the issue of what would you do if you're not doing greedy? Okay? Can have answers that are different from the normal U plus answer that we looked at earlier, where you just keep track of how many times you came to this state and make states that you haven't seen before look particularly attractive to you. Instead, we can do things that will only be doable because you happen to know the entire model. Okay? You can do things that that can be done because you have the entire model, and we'll get to that. Essentially, what will happen is in these kinds of scenarios, the way you update. So, because I happen to have the entire model, the first question is, how do I initialize the values for the states? In reinforcement learning, how do I initialize? I'll just put some random numbers. If it's MDP, how do I initialize the model? That's like asking, during A star search, when I don't know how far the goal is, what do I initialize my current estimate as? Yes, you can put 0, but you can do admissible heuristics. You can put straight line distance, that will be much better. So one thing that we will do, because we have the model, okay, we can actually generate heuristics, admissible heuristics, and use them to, first of all, initialize the value function. Point one. Point two, now that you have the model and you know that heuristics, a heuristic is actually sort of a admissible bound on the true value function. Admissible means it's less than. So because we're talking about SSPs, in the case of SSPs, H will be less than or equal to basically V star, because V is not a value really, it's the optimal cost. Okay, an admissible heuristic would be less than or equal to V star, And one of the things we can try is this is the lower bound. We can also get upper bounds of the values based on the model information. And then try to go to states which have large spread in the upper and lower bounds. That's a great way of making this greedy exploration even better. You see what I'm saying? Ultimately, I'm never going to tell you that if you have time, you should look at the rest of the world, because the whole reason we are doing this is because we want to focus our attention on the states that are likely to happen. You see what I'm saying? Okay? So you have to understand that doing exploration in this model makes not too much sense, because if you're doing exploration, in fact, I would say normal value iteration is full exploration. It's doing everybody every time. It can't miss anybody. In reinforcement learning, exploration is a big issue because you don't know the states and you don't know the action model. Here you know everything. And the reason you're doing this trace-based backup is because you want to just get your values for the states that you're likely to encounter correct faster. And so what I would do when I go away from greedy action selection is even more greedy action selection, wherein I would say I will try to look at those states where my estimate of their upper and lower bounds are so far, the spread is so high. So these are states that are likely to come in my path, but they have high spread in terms of my understanding of what their value is. So I spend more time figuring out. So I'll try to get them up first so that I will, get their value up. Okay. This is sort of a third order sort of an issue where you are actually you can do something more than greedy. I mean, there's a slides on this in this particular lecture. But you are essentially doing the improvements you're doing on greedy are to be even faster convergence of the policy.
This does depend on the stance.
Yes.
So what if I end up doing something like a safe where I can't reach it?
No. So the idea is in the big, so what we are doing here is the agent is always starting from S0. And then it will then learn the optimal policy for all the states it's likely to find from S0 to the goal state. And then if it finds itself in any of those states, it knows what's the right thing to do. So basically it's finding a partial policy, with the assumption that it always starts with a unique start state, which is not that bad. In many cases, we do know that you start from, flights, for example, take off from the airports, right? So there are actual start states available. Yes?
If my greedy action suggests me to go to S3 and the simulator says that I should be going to S2.
Greedy action, what?
Can there be a case where my greedy action says I should go to S3, S3, but the simulator says it should be S2?
No, your simulator is, so you select the actions. The simulator selects the outcome of the action. You don't select the outcome of the action. If you do that, then you're God, right? And you play God in computing heuristics. But you don't play God in actually getting the true value function. Okay? So for example, one can try to get like an upper bound on the value, for example, by saying whenever I do an action, the outcome corresponding to the state with the best current value would be the one that will happen. Okay? And I can do that. And I can basically use that to compute the heuristic. So anyway, this is basically the trace in this case. And let me just show you two things and then we'll be done here. So you repeat this forever. Okay? And then, so the question, of course, is there is no termination criterion. Of course, you can just keep repeating. And secondly, so could you improve on this? Up until here, whatever I told you, it truly is the case that you could either use, either you could have a model that you happen to know and you're just simulating it, versus you're just using the real world to figure out. This algorithm would work either way. So up until now, it's both a reinforcement learning algorithm and an MDP inference algorithm. Next, what I want to do is to try and see, given that I have information about the model, I'm just lazy. Okay, maybe I will be less lazy. I will look at the textbook once in a while during my studies. So can I improve the convergence of this approach? Without having to do large number of trials, can I reach the optimal policy faster? That basically gets us to an idea called LRTDP. And I will send you a paper by Geffner and Bonnet, which discusses LRTDP algorithm. It basically discusses the algorithm up until here, plus also how to keep track of the convergence. Okay. One idea is, for example, this guy has already converged. And if all my neighbors have converged, then I have converged. Even if all my neighbors haven't converged, if I am initializing my value function to be a lower bound on the true value function, and if my best neighbor has converged, then I have converged. I just said this. When you go back and look at the paper, you'll see that. So what you'll wind up doing is you'll start using the model to keep track of which of the nodes have already converged their valuation. Once they have converged, you can actually say my trace can stop as soon as it reaches a converged state. Okay, and when you actually wind up getting a converged label to the initial state, then you can say for sure I'm as good as the optimal policy at this point. You see what I'm saying? So for next class, we would actually come prepared having read Geffner and Bonnet's paper, and we'll just basically discuss that. Okay? Yeah.
Just a small question. In this example,
Mhm.
suppose the